Typically, the inner solar system only hosts a few comets each year. Yet come late 2025, a remarkable 7 significant bodies will plunge inward simultaneously. Among them, the interstellar giant 3I Atlas, which appears to be expanding steadily. Scientists are charting this extraordinary cluster, unmatched since the advent of contemporary observatories, as they trace the trajectories of these visitors hurtling by Earth and the Sun within a compact 6-month span. Experts speculate that the heightened activity might intensify solar flares, and perhaps one of these intruders could shine vividly enough to spot unaided. So, what prompts this sudden influx? And what levels of risk or awe might this celestial bottleneck unleash? We'll unpack the most exceptional comet lineup of our time. Witnessing 7 prominent comets jamming the inner solar system during one period is virtually unprecedented. In ordinary years, observers detect maybe 1 or 2 vivid ones gliding near for close examination, or occasionally 3 during fortunate sweeps. However, a single year featuring 7, all arriving in mere months, marks an anomaly that shines even across a century of records. From the launch of organized celestial scans like Pan-STARRS, Linear, and the Atlas Initiative, no interval has rivaled such congestion. The previous occasion when comet tallies neared these figures involved instruments still capturing images on glass negatives, with finds often stemming from chance sightings or hearsay. Beyond the sheer quantity, what's striking is the swarm's nature. Not a gradual drip spanning years, but a focused barrage where each participant weaves through the inner realms in quick sequence. Certain ones hail from remote outer zones, some represent recurring orbits, and 3I Atlas hails from beyond our solar system entirely. That rogue outsider would grab headlines solo in any season. Combined with 6 additional substantial comets, the probability shrinks to near impossibility. On average, since 2000, just 1 comet per year achieves visibility to the naked eye, alongside 2 or 3 more detectable via binoculars or scopes. Plenty of seasons pass with solely dim, far-off smudges. Even amid so-called comet bursts, short bursts of multiple arrivals, figures like 7 scarcely appear in recent archives. Per the Minor Planet Center's open records, no era in the digital age has accommodated over 4 key comets with closest solar approaches under 2 astronomical units, and that overlooks the ecliptic synchronization this batch displays. To put it in perspective, comet detections have surged lately thanks to automated sky patrols, yet most prove faint, remote, or fleeting. Those brilliant, approachable ones stay scarce. The 2025 surge stands out so sharply that some researchers label it a probabilistic freak, an occurrence perhaps limited to once every few lifetimes. Thus, this transcends a mere catalog of items. It's a bona fide spectacle, upending our assumptions about the solar system's standard cadence. Given the cluster of frozen wanderers converging so closely in time, experts view it as a unified, multi-phase spectacle. Attention has pivoted from solo profiles to monitoring their joint dynamics, how paths, positions, and sunbrushes could intersect or amplify. This uncommon overlap sparks both scholarly buzz and widespread curiosity. Prior to exploring specifics like perihelion, superior conjunction, and ecliptic positioning, consider the sheer improbability of 7 key comets co-starring simultaneously. See Tan-22 N2 Pan-STARRS kicks off the 2025 Comet Parade, hitting perihelion on July 31st at 3. 82 astronomical units from the Sun, its remote route positions it far past Mars, where solar rays weaken and only top-tier instruments can follow its journey. Pan-STARRS thus defines the swarm's distant edge. A subdued beginning precedes the truly spectacular entries. C-Tone-25 R2 Swan comes next in line. Spotted on September 11th and hurtling toward perihelion merely a day afterward on September 12th at 0.50 astronomical units, the real excitement builds on October 21st as Swan glides by Earth at a mere 0.25 astronomical units, roughly 37 million kilometers away. Such a near pass positions it as an ideal target for viewing, particularly in the northern hemisphere's pre-dawn hours. The comet's swift path and positioning provide a unique opportunity to observe its real-time exchanges with both the Sun and our planet. 400 Pisterio loops around the Sun on September 27th, achieving perihelion at 0.52 astronomical units. Its trajectory dips beneath the ecliptic plane, posing difficulties for Earth-bound observatories that frequently get obscured by sunlight. This comet, named after the Stereo mission, proves more amenable to imaging from probes. Its subdued path delivers a fresh perspective on solar phenomena. C-Tungsney 5 K1 Atlas makes its entrance soon after, hitting perihelion on October 8th at only 0.33 astronomical units tighter than Mercury's closest solar approach. This intense solar graze will trigger swift transformations in Atlas, turning it into a vital focus for tracking eruptions and tail formation. Positioned so near the Sun, it sits at the core of the comet cluster's dynamics. The interstellar interloper 3I Atlas attains superior conjunction on October 21st, slipping behind the Sun as seen from Earth. Perihelion arrives on October 29th at 36 astronomical units, right inside Mars's orbital path. With roughly 5 inclination, 3I Atlas stays near the ecliptic, mingling in the sky alongside planets and fellow comets. Over a few days, both 3I Atlas and Swan hold key spots for examining solar influences, even if spotting them proves tricky. C-Turutnei 5 A6 Lemon crests at perihelion on November 8th at 0.53 astronomical units. Its route ensures visibility in the post-sunset evening sky, granting one of the easiest viewing periods among the bunch. Predictions indicate it might brighten to magnitude 4 or possibly 3. 5, allowing naked eye detection for northern skywatchers in early November. 240 PNE wraps up the lineup, attaining perihelion on December 19th at 2.12 astronomical units. As a returning comet, it's dimmer and more distant, yet its appearance underscores the bustling inner solar system toward the close of the year. The trajectories, perihelion timings, and ecliptic ties of each comet forge a compressed schedule, priming the ground for ensuing solar engagements. Comet narratives extend beyond mere celestial streaks. They serve as dynamic archives of the unseen energies shaping the solar system. As a comet nears the Sun, solar heat warms its core, vaporizing gases and particles that create 2 separate tails, a wide, faint dust tail and a slender, vivid blue ion tail. The ion tail especially links straight to the Sun's magnetic influence, composed of ionized matter carried off by the solar wind, a relentless stream of charged particles and magnetic structures spiraling from the Sun at speeds of hundreds of kilometers per second. It doesn't endure forever. Abruptly, it can break away in what's called a tail disconnection event. This stems from magnetic reconnection processes. While navigating the solar wind, the comet may hit sudden shifts in the interplanetary magnetic field, such as from a coronal mass ejection or traversing the heliospheric current sheet. These shifts aren't smooth. The field might twist by 90 or greater within minutes. In those moments, the comet's plasma setup fails to adapt. The prior tail detaches, wandering into the void, as a fresh one emerges, precisely oriented to the updated solar wind flow. A striking instance unfolded in April 2007 when the Stereo probes observed a coronal mass ejection colliding with Comet Encke. The ion tail severed sharply, leaving a clear break close to the core, with the discarded section drifting free. A classic demonstration that aligned perfectly, magnetohydrodynamic models capture these phenomena nearly frame by frame. Such occurrences are quite common amid the solar maximum phase. Given that multiple comets will plunge close to the ecliptic toward the end of 2025, the chances of observing a disconnection in real time have never been greater. In comparison, the dust tail remains largely unaffected by these magnetic disturbances. It responds primarily to solar radiation and gravitational forces rather than magnetic influences. Merely the strongest coronal mass ejections can alter or shorten a dust tail, typically by eroding portions of the coma or altering the particle flow. For typical skywatchers, the abrupt fractures and subsequent reforms in the ion tail serve as the key indicator to monitor. This represents a vivid manifestation of the sun's turbulent dynamics unfolding over vast stretches of space, spanning millions of kilometers. Solar researchers are observing this cluster of comets with a blend of excitement and caution. And it's not merely for the visual display. In the background, a heated discussion is unfolding regarding the potential implications of these near encounters for solar activity. Certain study teams, particularly those from NASA's CCMC modeling group, contend that the abrupt influx of cometary plasma and particles, especially from comets aligned with the ecliptic might, actually provoke the sun into more regular or severe eruptions. Their computer simulations indicate that when a comet laden with material intersects the heliospheric current sheet or navigates through a coronal mass ejection, the magnetic configuration can alter swiftly, occasionally sparking a typical tail severance. Within these simulations, solar magnetic field lines envelop the comet, and should a CME arrive from the optimal direction, the ion tail could detach abruptly, often in mere minutes. The CCMC's magnetohydrodynamic analyses propose that multiple comets active during solar maximum elevate the likelihood of seeing several striking tail detachments, and the surplus plasma could further instigate fresh disruptions in the solar wind. However, skeptics abound. Teams operating the Solar Orbiter and Parker Solar Probe cite their coronagraph observations, asserting that the majority of tail disturbances are far milder than what the models forecast. They have documented numerous subtle distortions and curves in comet tails that fail to escalate into complete separations, even amid robust CME episodes. Their in situ readings reveal that fine-scale eddies, minor magnetic reconnections, and the inherent fluctuations in the solar wind often contribute significantly, sometimes outweighing the prominent CME effects. From their perspective, the sun's inherent magnetic rhythms and broad field flips constitute the primary forces at work. Comets, in this interpretation, function more as inert markers than influential players, leading them to warn against exaggerating threats to orbital assets or electrical networks. They highlight that during the 2007 Enki incident, the practical consequences were minimal. Nevertheless, as coronal mass ejection frequencies are projected to reach 2 to 5 weekly in the waning stages of the 2025 solar maximum, both sides concur on a single point. This presents an exceptional opportunity to validate their hypotheses live. Space weather authorities are intensifying surveillance efforts, while amateur astronomers gear up for a worldwide observation drive. Should a significant tail severance occur with a comet visible, spotters ranging from home setups to orbital instruments stand poised to document it. At present, the controversy is heightened vigilance across the board. Each fresh CME or peculiar contour in a comet's path might sway the balance in this persistent scholarly dispute. When scientists initially calculated the path of 3I Atlas, the figures defied conventions seen in native solar system comets. Its course follows a hyperbolic arc, boasting an eccentricity exceeding 1. This implies it's not merely a temporary visitor, but a transient interloper, destined never to circle back. That distinction alone marks it as exceptional. Just 2 prior intruders, Oumuamua in 2017 and Borisov in 2019, had been verified as extrasolar origins before it. Yet Atlas stands out for additional reasons. Initial scans from the Hubble and James Webb telescopes estimate its core spans roughly 320 meters to 6 kilometers in diameter. However, the surrounding coma, the envelope of vapor and debris it's releasing as it approaches the sun, has already ballooned to approximately 700,000 kilometers in breadth. That's on par with Jupiter's scale, and it's swelling further each week. In contrast to typical comets, which linger for ages, confined to the distant edges of our solar system prior to its sole close encounter with the sun, Atlas originates from a far greater distance, probably expelled from some other stellar system, bearing substances formed in a remote stellar region. Its makeup is distinctive as well. Spectral analysis shows a surrounding envelope rich in carbon dioxide and various volatile compounds, with minimal water vapor and only subtle hints of cyanide. Such chemical signatures appear infrequently in such quantities among native comets. The trajectory provides equally compelling evidence. It plunged into the solar system at a sharp inclination, grazing the ecliptic plane at roughly 5, with a speed that confirms its extraterrestrial source. The rewards for science are substantial. Every data point offers an opportunity to contrast the foundational elements of far-off planetary setups against those in our vicinity. Beyond mere composition, there's additional significance. As Atlas swings around the Sun, it sheds a stream of particles and fragments that our planet might intersect in 2026. This presents a unique chance for experts in planetary protection to examine interstellar matter in detail. The narrative of 3I Atlas continues to develop, yet already it's reshaping our understanding of the solar system's limits. Between late October and early November 2025, stargazers get a special viewing period for comets. No fancy gear needed, just unobstructed skies and good timing. The spectacle kicks off pre-dawn on October 21st as C-25 R2 Swan reaches its nearest point to Earth, passing at around Azuriciro. 25 astronomical units. Viewed with basic binoculars, Swan's tail extends impressively to 2.5, equivalent to 5 times the full moon's disk. Its nucleus shines at magnitude 6 to 7 dim, yet accessible to early risers searching the southeastern horizon. In northern regions, Swan rises to about 40 at civil twilight, ideal for dawn observations. At the same time, 3I Atlas will pass behind the Sun during superior conjunction. Though earthbound scopes can't track it, the focus moves to digital platforms. Instruments like Soho's Lasco C3 coronagraph monitor both 3I Atlas and occasionally Swan as dim specks amid the Sun's corona. These live streams are freely available. The public can participate in spotting abrupt shifts, flares, or potential tail separations caused by solar activity. Come early November, C-25 A6 Lemon takes center stage after dusk. Predictions suggest magnitude 4 or perhaps 3. 5. Visible unaided from dark locations, particularly in the north. Positioned low in the southwest post-sunset, Lemon's envelope and tail grow more vivid nightly, approaching perihelion on November 8th. For numerous observers, it'll mark the simplest comet sighting in ages. Whether peering through binoculars, a small telescope, or bare eyes, this period invites venturing out to observe the solar system's dynamics. Prime viewing falls on October 21st for Swan's approach and November 6th to 12th for Lemon's peak. For those obscured by the Sun, global coronagraphs provide access via a simple web link. Predicting comet visibility teaches caution. Despite abundant information, annual estimates can vary by up to 2 magnitudes or greater. A body anticipated to shine at magnitude 3 might dim to 5 or 6. Conversely, a subdued prospect could flare unexpectedly, surpassing forecasts. These twists stem from unpredictable elements beyond any simulation's grasp: dust particle dimensions, ice compositions, sunlight's interaction with a potentially thick outer layer. Even sophisticated thermal models can't account for minor variations in solar warmth or concealed cracks that alter outcomes swiftly. For 3I Atlas, the unknowns are profound. Its core might measure just 320 meters across or stretch to 5 kilometers. Limits from Hubble and JWST observations narrow the possibilities, but the actual dimensions evade confirmation. The envelope's prevalence of carbon dioxide. Although spectral analysis provides some clarity, a comprehensive catalog of volatile compounds and particulate matter remains elusive. Lacking robust evidence for water or conventional gases, each fresh batch of observations continually refines prevailing hypotheses. One indisputable fact is that predictions will keep shifting through perihelion and well afterward. Turning to the future, upcoming observational programs, particularly the Legacy Survey of Space and Time from the Vera Rubin Observatory, are set to uncover additional surprises. Systematic scans across the entire celestial sphere will detect dim, swift transients that currently evade notice. Yet, even during the LSST period, discoveries will owe as much to unforeseen events as to theoretical projections. At present, the wisest approach is to observe the heavens receptively and brace for surprises. 3I Atlas, featuring its enormous carbon dioxide envelope spanning more than 700,000 kilometers, distinguishes itself through its extrasolar roots and enigmatic makeup. As scientists persist in tracking such visitors, the cluster arriving in 2025 will challenge and broaden our insights into cometary dynamics and their engagements with the Sun, contributing fresh insights to the evolving narrative of our solar system.